Hello, everyone. Thank you for having me. Yeah, I think you describe what I do quite well. I mostly spend my time complaining about things on Twitter and maybe sometimes just argue with people about definitions, but that's mostly what I do. And today I'm going to be talking about sequencers and asking a question that I don't think a lot of people have asked until now. Do sequencers actually matter? So let's start with a short answer. No, they don't matter. Thank you. That's it. No, I'm joking. Uh, yeah, you probably heard about what rollups are. So before we go further, let's explore what they actually are because I think Bartek is sitting here and like looking at me like I think we have L2Beat has a great definition. But yeah, anyways, I'll try not to disappoint L2Beat here. So on a fundamental level, a rollup is just a protocol that publishes data on another rollup, on another protocol. So specifically, you need to publish enough data that allows you to reconstruct the state. So essentially, you need to be able to later either transact or exit the rollup in case something fails. But let's go into more details. Through the publication of data, rollups inherit the following guarantees from the base layer. And the base layer, when I refer to base layer, I mean the layer where the rollups publish their data. First is ordering. Pretty simple. Ordering is just we take a certain sequence of transactions, define it, like transaction A comes before transaction B, etc., 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 publish it to the base layer, and then it guarantees that you cannot, after it's finalized, you cannot take it and just say, oh yeah, actually transaction B comes before transaction A. And that's a very important property because as long as Ethereum or any other underlying base layer functions as intended, there's no way you can later just like say, oh yeah, the ordering that we publish is completely incorrect. There's a new one. Another one, which is the side effect of publishing data, is data availability. And data availability is basically a property where the protocol that just ensures that the data is made accessible to anyone who's willing to download it or is interested in downloading it within a certain period of time. And you need to make sure not confuse it with data publishing, which is the process, so data publishing, that is the process of making the data available for a prolonged period of time or forever. And then the last property that rollups enable is censorship resistance. It's quite difficult to define censorship resistance in form of one slide. So let's just abstract from now and assume that censorship resistance is a guarantee that a transaction received at block T is included by block Tn by the sequencer. And so essentially, we guarantee that as long as the transaction pays enough, it'll be included within a certain period of time. It's a bit more nuanced than this, but let's just ignore it. It's boring. And then we can also deploy a validating bridge on the underlying base layer. And if we deploy a validating bridge, the rollup becomes what I like to call a classic rollup. And a classic rollup inherits an additional property. Basically, the validating bridge allows us to inherit the validity guarantees of the underlying base layer. And yeah, you can see that I put a bit of a addendum here saying terms and conditions apply, and I'll explain what I mean by that. So what's validity? Validity is basically the property, the protocol property that we define. So let's say if we apply transaction A where Bob sends 10 ETH to Alice, when we execute that transaction, the outcome of the state has to basically apply those changes. And that's called the state transition, and validity guarantee essentially ensures that the protocol rules and those state transitions are applied correctly. And the terms and conditions in this case mean that the validity can be enforced only under the assumption that the underlying proof function as intended. So in this case, it'll be in an optimistic rollup, it'll be a fraud proof, and in a zero knowledge rollup, it'll be a zero knowledge proof. So we need to assume that they are correctly implemented and functioning correctly. So there are two types of classic rollups. optimistic rollups, and zero-knowledge rollups. And I'll just add that in case there's anyone from Starkware, because they just refuse to acknowledge that there's a thing called zero-knowledge rollups, and they refer to them as validity rollups. So typically in optimistic rollups, you have 3 explicit protocol roles. So you have a sequencer, which is just responsible for proposing eliminatory transaction orders. So basically, it picks up a bunch of transactions from the mempool, propagates it, and says, yeah, this is the preliminary ordering. Executors, which apply that ordering and derive the state from it, and then publish the state root to the validity bridge, validating bridge. And then challengers, who follow the state root updates, and in case there's anything wrong or an invalid state root is committed, they challenge and basically prove to the validating bridge that actually the state root that was committed was incorrect. And those roles can be interchangeable. The hardware requirements are roughly the same. So a sequencer can also be executor or a challenger. They all run full nodes. So in a typical scenario, you can make a sequencer run without a full node, but let's assume for now that they do. And then in zero-knowledge rollups, we define 2 explicit protocol roles. So one is sequencers, same as before. They just propose a preliminary ordering. And then we have provers, who are responsible for computing validity proofs. So what are validity proofs? Validity proofs essentially use zero-knowledge proofs to assert that a certain state transition was done correctly. Essentially, again, back to the scenario where Bob is sending 10 ETH to Alice. The validity proof would essentially prove that actually, yeah, the end state that the state root that we propose at the end is actually correctly executed. And the hardware requirements in case of zero-knowledge rollups are actually quite different. So provers are usually going to be quite compute heavy. They're going to use a lot of GPUs, etc., a lot of memory, depending on a specific, or sometimes even ASICs. Whereas a sequencer is same as with optimistic rollups. It's just a full node. There's nothing more to it. So a sequencer can never be a prover, at least currently. There is a future where provers are efficient enough when you can use it on a normal machine, but not for now. And then, but conversely, a prover can be a sequencer because the prover still has to run a full node in order to check that the state transition is correctly applied, and then to input those, basically the execution trace into the proof to be able to compute it. And so, let's focus on zero-knowledge rollups for now. Sorry, it was quite a long tangent, but now that we're here, I think we can go into the nits and grits. So imagine a scenario in which both the sequencers and the provers are decentralized in a ZK rollup. Let's say you have a set of 1,000 provers and a few hundred sequencers running simultaneously in a rollup. And it's likely what's going to happen is that the sequencers just outsource block production to some external builders. So what happens in Ethereum, for example, you have thousands of validators. All of them can be selected as proposers for a given slot, but because they don't have the special capabilities of optimizing the extracted value from a given block, they just source it to some specialized entities called builders, and they just construct the blocks for them, which is a win-win scenario because the builders are usually quite good at it, and the leaders get to earn more money because the builders know how to optimize the extracted value. And it's likely that the same is going to happen here, where the sequencers are just going to outsource it to a few builders and say, yeah, do it for me. Give me as much as, compete with one another, bid as much as you can, and I'll include your block instead of building it myself. But then a good question arises. Why do we need sequencers? They're just middlemen between builders and provers because what they're doing is they're not constructing anything. They're just outsourcing the block construction to some external entities, or you can even internalize builders. And then the provers compute the proofs. So why do we need the sequencers? Yeah, you can argue that you can get pre-confirmation from them, but you can also just use provers to pre-confirm. So yeah, why not just remove the middleman? the protocol leaks less value, and also it helps with achieving balanced incentives. And what I mean by that is, in the initial setup, assume that like there's a decentralized sequencer and approver, because the sequencers have exclusive rights over the ordering, and it's likely that in L2's MEV is going to be a large portion of the protocol value accrual. They keep the majority of the incentives, which means that there's a potential scenario where people are just not incentivized to become provers because it's just not as profitable, and the incentives become quite lopsided because the sequencers get most of the incentives and then the provers do the most expensive work because computing validity proof is quite expensive. And so there are solutions to this. So for example, you can optimize, you can adopt PBS to work with it, but then again, if you assume a scenario where sequencers outsource the block building, then you essentially end up with PBS inside PBS, which is not great because you're leaking so much value there. And so how do we remove a sequencer role? You just assign the sequencer role to the prover. The prover is already running a full node. The prover already has enough hardware to do that. The only difference is that you might, in case you run a classic consensus protocol, you might need a bit of a stronger network connection, and that's it. So let's say that we have like a setup where you have a decentralized prover, and per block you just elect one prover, assume that there's a leader election function who's responsible for both proposing the block and computing the corresponding validity proof. And you might have a question, what happens if that prover doesn't submit the proof in time? Because we can't just wait forever for every proof to be submitted. Well, you just set a certain time limit. So I don't know, let's say 10 minutes or 15 minutes, depending on how much time it takes to compute the proof. And then once that time elapsed, you can either assign a new prover, or another way of doing it is doing like a competitive setup where the prover essentially competes. Every prover competes with one another to submit the proof. But that's not very efficient, so you can as well just reassign to a different prover, and that prover gets to keep the rewards for the block that the previous prover proposed. And you can essentially continue that process iteratively until a successful validity proof is published. And in this setup, the builders can either be enshrined or they can be extra protocol, which means that they can either be part of the rollup, or the protocol specification is not aware of of the existence of builders. They're completely external to the protocol. Think of how PBS works in Ethereum today. The protocol has no idea that the PBS is even there, and you can just choose to build the block yourself and not outsource it to anyone. And we can, let's say we use a classic consensus protocol, I don't know, hot stuff, whatever. We can even increase the messaging overhead somewhat by pipelining it. So you can, because it's a bit of a concern, because let's say that we need quite a lot of provers, and it's likely that you will need hundreds, if not thousands of provers to parallelize it enough. Then the problem becomes, how do you handle so much messaging? Well, you can somewhat decrease the messaging by pipelining the consensus protocol. And also, think of it this way. Currently, Ethereum handles around 3,500 votes per second. So I think it's not very far-fetched to assume that a classic consensus protocol can also handle hundreds, if not thousands, of votes per second. And by default, unfortunately, this design, or any design with where a few centralized builders are involved, have weak real-time censorship resistance guarantees. And by weak, I mean that, by real-time, I mean that basically within a short period of time, there's almost no guarantee that a transaction will be included, because those builders can either comply with OFAC sanctions or something else, and just refuse to include blocks for some period of time. Of course, with the rollups, you can always force include the transaction or a batch from the L1, but then it'll take some time. And for certain use cases, that's just not good. So think of like an Oracle update. You cannot wait for 10 hours before an Oracle update is actually inserted, because by then it might be that the protocol becomes under collateralized because the liquidation point has already passed. And so we can also adopt the Ethereum approach that Ethereum is currently working on, which is called CR lists, where essentially the validator set votes on the certain transactions once in a while, and the proposers are required, the builders are required to include those transactions within a certain period of time. Or we can even do partial ordering proposal. Because we have finality, because if we use a classic consensus, we have finality, we could adopt this approach and just have part of the block proposed by the builder and part of the block proposed by the proposers themselves and just combine them together later. And we will have a more detailed write-up of how this all works published soon. I don't want to say when soon, because in crypto, usually when you promise a certain date, it usually always gets delayed, so I'm not going to commit to certain dates. And yeah, just a disclaimer that this is not a final design that we're going to use, and we're still experimenting with it, and once we publish, we're going to consult with the community and different experts in the field to see whether we can improve it or even have a completely alternative solution. So in conclusion, just one last thing. A decentralized design in which sequencers are likely to outsource ordering, block construction, to externalize parties. Essentially in this design, sequencers are redundant. You just don't need them. They're middlemen connecting the provers to the builders, and so why not just remove them and let the value accrue more efficiently. Thank you very much, and if you have any questions, feel free to ask. Can I have a microphone? Oh, I think they're giving you the microphone.
So, a very quick one, right? On the last slide, if you outsource block construction to external specialized parties, then you just replace one middleman with another. So you still have middlemen.
Yeah, you have middlemen, but now you have one middleman versus two middlemen. So it's better than. So essentially, you can just have the provers construct the blocks themselves, but they're unlikely to specialize in MEV, and so it's just more effective in terms of how you accrue value to outsource it to specialized middlemen, if you want to call them that.
Thank you for your talk. I just wanted to ask about this construction at the end, about provers, how they, like, there's a leader election and stuff. Why don't, it's maybe a stupid question, but why don't you just use like proof of work scheme? Basically, like, this kind of proof generation is similar to, you know, proof of work. Can you just use the vanilla consensus algorithm?
You could potentially use it, but there are a few downsides. So a lot of people assume that having competitive proving, so emulating essentially Bitcoin and using like proof of work style competitive proving to computer proof renders similar results to Bitcoin, but actually it's extremely centralizing because proving is deterministic, so there's no randomness involved. So the most efficient prover will always gonna win. And therefore, in a long-term scenario, you end up with just one or a few provers participating, which is not really good in case something happens and that prover fails, for example. And also, if you want to parallelize proving, which we kind of have to because prover times are slower than the block times, competitive proving doesn't really work well because you either have to like assign certain groups of provers to different proofs, but then you might as well just assign a single prover and then have fallback in case they fail to submit within a certain period of time.
Okay, and the second question, because like this conference name is hot takes, like not a lot of hot takes today, so I would like to ask, is the rollup a rollup if it doesn't have, it doesn't use native data availability layer?
No, it's not. A rollup, the name essentially means that you have to have post the data to the underlying layer. If you don't, it's not a rollup.
I mean, like Arbitrum Nova, is it a rollup?
No, it's not.
Okay.
It's an optimium. Bartek can correct me, but I think it's an optimium. Yeah, I think it's optimium now. Yeah, It used to be Plasma, then it was Optimistic Chain. I think it's now called Optimium.
Okay, thank you.
Thank you.
Thank you. So this was very convincing for the scenario of one rollup with very decentralized sequencers and provers. So I want to ask you, how do you feel about another scenario in which you have shared sequencers between many rollups? Like, do shared sequencers matter because they're easier than shared provers, or does it change anything in your way of thinking?
It depends. I think shared sequencers are useful for certain things, but they're also not as useful as a lot of people think. So, for example, at least for me, one of the main use cases for shared sequencing is atomic inclusion, which means that you can guarantee that two transactions can be executed one after another in two different chains. But the downside is like quite big. There are two problems here. So let's say you two rollups use a shared sequencer. One is an optimistic rollup and another is ZK rollup. The ZK rollup's finality now becomes equivalent to optimistic rollup's finality, which means that at that point, why would you even use ZK? You might as well be optimistic. And then two, let's say if you want to run a full node and just rely on the off-chain finality when the data is published on-chain, then you essentially, and let's say there are 10 different rollups using a shared sequencer, you essentially have to run full nodes for all of them to have this finality, which is also not very useful. But there are certain reasons why you would want to have a shared sequencer. So for example, if you're building a certain app-specific chain and you just care about the application and don't want to deal with all the infrastructure, etc., then it's completely useful because you just outsource it to the shared sequencer, they do their job, and then you just worry about the UX or like the features that your app has. So again, it just depends on what scenario we're talking about.